a lot of windows to show here. So the first thing I wanted to show is how to get to essentially the answer key, or not the answer key so much, but the decoder for which mystery system corresponds to which real system.
BJ, could you make that window a little bit bigger, or the text in the window a little bit bigger, please? It's really small. Yeah, that's better.
That's better?
Yeah, better, thank you.
Okay, so if you go to the GitHub repo, and then again, you switch over to the answers branch, and then you click tutorials, there'll be the answer key here. So I've given the real system here, I've given a reference, sometimes it's a discovery reference, sometimes it's like a recent update reference. It's not the definitive reference for these systems, but it's a good starting place to go to start digging into literature to see the history and other references that may refer to this one. Okay, so I'm going to go through each of these systems and your responses on the Google Forms, and we're just going to kind of do this in real time and see what you guys came up with. So system 1 is HD20794. There are at least 4 planets there. I'll make this bigger too. There are some indications that there may be further candidates as well, but here are the confirmed planets. So we have an 18-day, 40-ish day, 90, and 150. So let's see what you guys came up with. We had 33 responses on this one. And the majority of people found 2 planets, okay? And only 1 person found 4. Now, it's a little bit difficult to tell if this 1 person found all the right 4, but let's look at the first couple planets anyway. So the people that found the first planet, 10 to 30 days is the range for the majority of people. So I think that's correct on this first 18-day signal. Period of planet 2, 30 to 100 days. So I think, again, that people are mostly finding this 40-day signal second. So that's good. Period of planet 3, 30 to 100 day range, I think. So the people that found that were getting the period right at 90 days. And then the longer one. So the 1 person that found 4 looks like they found the final planet at 300 to 1,000 day range. So not quite the 150 days. So maybe they found double the period or a yearly signal instead. So eccentricity, it looks like all of these planets are low eccentricity. So when you're browsing the data and the results for these, you may see significant eccentricity values like this. But if you notice, the lower uncertainty is -0.22 here. So that makes this only a little bit more than 1 sigma, which is not really a significant eccentricity. Basically, all of these are circular. And so this is something I wanted to point out. So in these multi-planet systems, it's really easy to find more eccentricity than is real. So really be careful when inspecting your posterior distributions for eccentricity. And if it's pushed up against 0 at all, it's most likely that it's consistent with 0. So there's a lot of ways to bias yourself away from 0 eccentricity. Okay, so most of you guys got low eccentricity though in the 0.2 to 0.4 range, except for maybe this outer one. I wonder if that was a yearly signal. I'm not going to go through the semi-amplitudes and masses because I told you guys to assume 1.0 stellar mass, so it won't be exactly right with what the data shows. And so I encourage you that if you're interested, go back, recalculate that now that you know what system it is using the real mass and see how close you were to the right answer there. So let's just see if there's anything interesting in the notes here. A lot of long period peaks after 1,000 days. It looks like maybe it corresponds to S value. That's probably right. Yeah, so this person did a little bit more detailed analysis to find that the circular and eccentric orbit cases are both kind of valid, but circular orbit is preferred. That's good analysis. And then this person said spurious signal at 18 days due to a stellar rotation of about 30 days. So this person thought that 18-day candidate was activity, but it is published as a planet in the literature. Doesn't mean it's 100% right though, because it's not a transiting planet. So we don't actually, the community isn't 100% sure really on any of these, except for ones that are transiting perhaps. Okay, so that was system 1. Let's go on to system 2, figure out which one it was. So that is HD 10180. So this one has a lot of planets, 6 planets. And the responses were kind of all over the place on the number of planets found, but most people found 4 or more. The vast majority of people found 4 or more. So that's good. They found a lot of planets here. It's pretty difficult to get all of them. Let me scroll over the period here. Okay, so the people who found planet 1, it's all short period, pretty much 70%, it's pretty good. Again, about 70% found the next one 10 to 30 days, which is right. Planet 3, 62%. Found 30 to 100 days, so we're starting to lose a few percentage points, but not too bad. Period 4, 100 to 300 days, and that's 122 days probably. And then again, as we get to these higher ones, some mislabeling could happen. Some people may have missed one, and so these may be referring to, these people may be referring to the previous planet, the 604 day, and then these ones may be finding the 2000 day. So that's the 6 planets that are known. Again, I believe these are all low eccentricity. Perhaps planet 2 might have some significant, and planet 4 might have some significant. Let's see if anyone found that. So 0 essentially for 1, 2. Okay, so not, maybe one person found some eccentricity for planet 2. Otherwise, pretty much everything is circular until you get to planet 5, which may have some eccentricity. Actually, it's like a 2 sigma eccentricity there. And then planet 6 is probably circular as well, and most people found that. Semi-amplitudes are, oh, I don't have this up on this column. Let's add that. Just gotta find that column that I added. Here we go. Okay. So they're all pretty much, they're all, you know, in the 3 to 10 range, looks like, except for maybe one is a little bit less than that. Planet 1, 2, so 0 to 3, actually that's technically correct. It's right on the 3 boundary. So that's pretty much everybody got that right. Again, that's good. Planet 4 is 2.8. So yeah, again, right on that boundary, probably, you know, within uncertainties that's in both of those bins. Planet 5 is going to be 1.7. So that one's a little smaller. Most people did find it in that smaller bin. And then again, this one is kind of on that boundary at right about 3. So let's go see if anyone had interesting comments in the notes. We have a lot of notes on this one. I noticed that one person conjectured that this was 10180, so they found that. Periodic signal at 607, but just above the 1% FAP. Weak activity correlation for a period around 4,200 days. I noticed that several people found that this 2,400 day signal was S values or activity rather than a planet, but it is published as a planet in the literature. Yeah, so a lot of people found that this 2,500, 2,200 day signal was activity. All right, let's go on to the next one.
I think someone has a question, BJ.
Oh yeah, go ahead. I can't see that. So.
Yeah, BJ, I have a question. So, whenever you are getting like, is if I do not know a system particularly, just with periodogram analysis, can we tell whether it's a planet or not if we do not know the system? Like when I was dealing with the system 2, this I found the signal at 2205, but I was not sure whether that was due to a stellar activity or not. So, is it possible if we do not know the background information of the star, is it possible to determine whether it could be a planet or it's a stellar activity?
Yeah, I mean, the ways to do it are going to be to look at the activity indices, which I believe you had for system 2. The system 3 was missing those. But yeah, so look at activity indices, see if those show the same signal at the 2200 days in this case. You know, if they do, then that is definitely concerning for your planet candidate. You can also look at the stability of the signal over time, although for the long period signals, that's a bit difficult because you probably only have a couple cycles of it. But you know, there's never, it's hard to be 100% certain, you know, and when you're doing this for, you know, a new discovery of a new planetary system, it's going to be difficult for you to determine what's due to planets and what's due to activity. So you have to just basically try to look at as much external information as you can, activity indices, bisector spans, full with half max, in order to make an educated decision on what you think that planet is. And as we get to system 4, there'll be an interesting kind of background about that kind of situation in the literature. So I hope that answers your question to some extent. It's not really a clear-cut answer though. It's a difficult problem for all of us to try to figure out which ones are planets and which ones are activity.
Yeah, got it. Thank you for that.
All right. System 3, I believe this is Koros 7, yes. So this is an interesting one. So it has one transiting planet with a very short orbital period of 0.8 days. Nathan, does DACE even by default search periods that low?
Sorry?
Does DACE search for periods that low on the web interface for less than 1 day?
Yes, yes. And actually, you can find it even without fancy analysis with Gaussian process.
Okay, yeah, that one's pretty large signal. So there's a transiting one at less than 1 day, 0.85 day orbital period, and then a non-transiting one at 3.6 days. Now there's some history of other planets in this system, and that has been found to be activity. So let's see what people came up with here. So there's 2 planets. The responses were kind of all over the map here. 1 planet for 37, 0 planets, 28%. That's the only 2 people said there was 2 planets here. 3 would be an understandable answer. 2 people found that, and a few people found even more, 6 or more, 10% of people found 6 or more. So this is a pretty tough one. The activity signal is large. So period of planet 1, most people found 10 to 30 days. So that they're probably finding the rotation. Nathan, do you recall the rotation period off the top of your head on this one? I think it's 23 days, yeah. So I think most people that were finding this first planet here were actually finding the rotation period first. I believe that's the largest signal in the data, so it's not that surprising, but that is rotation. And it's pretty difficult in this one to disentangle from the planets because it's relatively stable. Period of planet 2, 3 to 10 days. So I think, yeah, the second planet most people are finding was this 4-day signal that was detected in random velocities. So that's good. And then I didn't even have a bin for the shortest period one. I didn't realize that until right now. But I don't see anyone was detecting in the 1 to 3 day bin even. So let's see if anyone noted that they found a short period one. It doesn't look like anyone found the very short period planet in the notes. Some people did find rotation period at 22 days. So that's good. But let's continue to go through these. So eccentricity of planet 1, again, people found significant eccentricity for this one. I don't think it has any, no, it's circular. So again, it's pretty easy to bias yourself away from zero eccentricity. Always look at your posterior distributions there. And the eccentricity of planet 2, which, so some cases, these are both mostly talking about either the rotation period, I think, where most people planet 1. So that's another kind of red flag sometimes. When you detect the rotation period as a planet, you'll often get high eccentricity value. And especially if you were detecting a multi-planet system and you think you found a planet, you know, at 22 days, and there's ones on either side at 50 and 10 days or something, the one at 22 days with high eccentricity probably is the rotation period. And you can check that with dynamical analysis or something as well to see if a planet with that high eccentricity would be stable. But the eccentricity sometimes eats up the fact that the signal is not totally stable over time. And so that'll manifest as a little bit of eccentricity if you're fitting it with Keplerian. Okay, let's go to centimeter axis. Planet 1, 10 to 30 meters per second. So you see that that's a pretty large signal, that rotation, and then a smaller 3 to 10 meter per second signal for that 4-day planet. I think that probably covers the interesting stuff. But so the history of this system is that there was originally 3 planets announced, I believe. So that 23-day signal was announced as a planet at one point, but then later found that that was activity. So mistakes like that do happen. And system 4 is an even further illustration of that. So this is Alpha Cent B. I don't have a good page for that because it has 0 planets. But I do have this. It's historical page for Alpha Cent B, and planet status is retracted. So most of you found 0 planets. That's good. A couple found 1. That's understandable, and 2 and 3. And the period of planet 1. This is again a very short period planet, 3.2 days. So it should have fallen in this red bin. It looks like the periods are kind of all over the place on this one though. This is a really challenging data set. And the history here is that there was a planet detected at 3.2 days in 2012. And then it was later found that that signal is actually due to aliasing, or a window function combined with stellar activity at longer orbital periods. And so that 3.24 signal goes away if you properly account for stellar activity at longer orbital periods. So let's see, since there's not really any planets to go through here, let's go straight down to the notes and see what people said. Linear trend in data. No planet, but a trend in the RV, and activity signal in about 1400 days. Yeah, challenging data, agreed. It is a binary system, yeah, and that's probably what's causing that long-term trend. And 2 objects with higher masses, interesting. No planets, okay. So yeah, go ahead.
A comment in the chat that for this one, Days claims there isn't enough data for activity indices and correlations. Why is this?
Yeah, I noticed yesterday, I think, that some data was missing, and there should be complementary data now on the system 3. So if you struggle with it, I'm sorry. I should have checked that all the data was there.
System 4, though, was missing activity as well?
System 4? No, I don't think so. System 4.
It said, yeah, so the comment was that that Dace was saying there was not enough data to do correlation analysis?
Yeah,
right?
I'll check. I'll have a look at it.
Okay, I don't know. That would make this even more challenging. So this is a system that you really have to be careful with stellar activity and look at the indices. And even then, it's pretty difficult to get the planet right. As you can see from the literature, it was not initially done right.
That comment was for system 3, not system 4.
Okay, yeah. System 3 was missing the activity indices, and now you say it's added, Nathan?
Yes, some data has been added with
Yeah.
activity indicators.
Yeah, so you could go check that out again and see if it would have helped your responses. All right, and then we have one more system, which is GJ876. Again, this is another really challenging one. So let's sort by orbital period. Okay. So how many planets? So there should be 4 planets in this system. Many people found 6, 6 or more. I will admit that if I search this planet blindly, I also find 6. So that's an easy result to get. 5, 10, 31% got 5. Let's see if anyone got 4. 1 person got 4. A few people got less, a little bit more conservative. Yeah. Period of planet 1. This is a short period, 2 days. So most people have found that, got that period right. Period of planet 2 is 30 days. So again, it's on that boundary. So between green and orange, pretty good. Next one is 60 days. So people started to fall off here. I wonder if they missed planet 2 maybe, and we're assigning it to planet 3. Planet 4, so the last planet, we have 124 days. So a lot of people found a long period planet, longer than 3,000 days. And that's probably activity going on at longer periods. Eccentricities, all of these are going to be very circular. So I think that that's pretty much right. Everybody got very low eccentricity for this system, so that's good. These are all pretty low semi-amplitudes in these 2 first bins. So I think that everybody pretty much got that these are small. Semi-amplitude of planet 3 is a little bit larger. Let's see. Well, that is a larger mass planet, so that's going to have a higher amplitude. That's right. Planet 4, again, we're getting larger amplitudes, but sometimes these are probably confused between these 2. And then planet 5 and 6 are not real, so we'll skip this. Okay, let's go look at the comments and then we'll discuss what's really going on with this system. Highly suspicious of these planets. They all happen to be harmonics of each other with 120, 90, 60, 30, 15, and 10, and 2. Weak correlation with a couple different activity indicators. But even after returning, most Keplerian fits have exceptionally low false alarm probabilities. Yeah. Huge resonance chain. However, the last planet, not sure which one they're talking about, found only when fitting the jitter with a specific number of planets already in the fit. So that's strange. Maybe a 6th planet at 124 days. Yeah, that one is. Well, it's not the 6th, but that is a planet. Stellar activity at 110 days. I'm not sure if that's correct. It might be. Too much information to submit. Interesting. Period of the S index shows 90 days. Looks like system has massive planets. So I wanted to show, if I could, what I would find here. I thought I had it up on one of my tabs, but let me get back to it. The interesting thing about this system is that it has a lot of planets and they're all interacting with each other. So you can't actually just assume Keplerian, a sum of Keplerian orbits in this case. So here was what I would find. This is probably too small to read the text, but that's not too important. So 60 and 30 days, these ones are pretty obvious. I just helped the algorithm find those first. But then you find 15, a 2, a 10, and 44. I believe 44 is rotation. But yeah, so there's 10, 15, these are all pretty easy to find. They're all harmonics, as was pointed out. And the issue is that since these planets actually are interacting with each other, there's going to be residual periodicity at other periods, at harmonics of the real planet periods. So there is a real resonance chain here. So really planets at 60 and 30 days. And then there's also these mistakes. It's easy to make mistakes and find extra planets at further harmonics because the planets are actually interacting, which then injects another periodicity into your rate of velocity. So it's really difficult to get this system right. And really the only way to do it is to incorporate an n-body simulation or model into your analysis. It's been done by a few people in the literature, and Nathan has worked on this system a lot too, so I don't know if he wants to add further comments, but it's a real challenge.
In fact, if you simulate just the 30 days and 60 days planets, which are two high-mass Jupiters, and you put this in input of an n-body simulation, and you compute the parallelogram of the simulated radial velocity, then you find peaks at 15 and 10 days. So that's how you can show that it's compatible with the two planets model. And if you wanted to go further, you can do a model comparison of n-body simulation and several Keplerian signals, and you see that the model with 4 planets wins. But that's a very computationally challenging problem to solve.
I think you'll also get a period at 9 years, the precession period of the planets.
Yeah, exactly. Yeah, and in fact, just with the parallelogram, you can find this the precession period very precisely just by computing the difference between the frequencies.
Yeah, it's a challenge. Do you remember if the stellar activity is are these 90, 110 day signals, or is it shorter period rotation?
I think there is a planet at 120 days. At 110, I don't know. I
Okay.
have to check it out.
Yeah, I think that the rotation is like 45 days. I mean, it could be 90, and I detected half that. Yeah. So this is a really interesting one, and entire PhDs have been devoted to studying the dynamics of the system. So don't worry if you did not get the right number of planets for this one. Okay, so in the last 3 minutes, I wanted to allow anyone else to talk about any challenges that they faced while doing this, or any interesting things that they found. So, or if there's any more questions, I'm happy to answer those as well.
There are a few things in the chat, which you might not be able to see, BJ.
No, I can't see that.
Let's see. Gosh, I don't even know where to start. I don't know. Why don't people unmute and ask your question? Is that, unless it's going to be too chaotic?
They can unmute themselves, right?
Okay, let's see.
Hello, BJ.
Mm-hmm.
Go ahead.
Yeah, so in the system file, there was an option regarding the minimum mass. And so I wanted to know about the minimum mass of the last planet detected in the system 5.
System 5. Okay,
Yeah,
let's look it up. Let's see, minimum mass. So this is the 124-day signal.
Okay, yeah.
3.42 Earth mass.
Okay.
So
Okay.
pretty low mass. Okay, well, anyone
Maybe
have
one-
last questions? Go ahead, Nick.
Yeah, maybe one last comment. First is, if you didn't find 4 planets for system 1, I think that's fine, because if you do the night binning, and even if you do a fairly complete analysis with the data that is on days, it's you find 2 planets. So don't feel bad if you haven't found the 4 ones. And you mentioned several times the problem with eccentricity, and if you're interested, I can send you a paper I wrote about determining whether the eccentricity you fit is real or not. And there are a few subtleties about this.
You should post that in the resources section.
Yeah.
Okay, so I wanted to let everybody go and get to their lunches, which start right now at 9. So I am happy to answer more questions or continue discussion on Slack if you like. I'll be around today to answer the questions, but I hope you had fun hunting for the planets and learned some things about basically how difficult it is to get this right. And the entire community faces these same sort of challenges that you did. So thanks everybody for participating.
And I just wanted to add another thank you to Nathan and BJ and Chad and Heather who put all this together, and the DACE team. This was great. Yeah, thank you so much. I know there's a lot of work that went into this.